Yesterday we have seen De Morgan's laws and proofs. Okay, let us move. Intersection distributes over union. So A set A intersection union I goes from 1 to n bi is equal to union I goes from 1 to n A intersection bi. Okay. Prove LHS is equal to RHS. Okay. Let us prove LHS is subset of RHS and RHS is subset of LHS. Therefore, every step that we are writing now is if and only if. So we are trying to prove both simultaneously. So meaning of LHS. So suppose an element X belongs to LHS, that is A intersection union I goes from 1 to n bi. What does it mean? It means X belongs to A and X belongs to bi. Let us write down X belongs to A and X belongs to union of I equals 1 to n bi. Because of intersection, we are putting the word and. Okay. Now we say what is the meaning of union? We keep it as it is. And X belongs to union. That means X belongs to bi. What should we write? Because it is in union, it should be contained in at least one bi, or at least one I. One is less than I is less than n. Therefore, it will be included in the union. Okay, so it is in A and it is in at least one bi. What does it mean? It means X belongs to A intersection bi. We combine this and now in the sign intersection for at least one I. Such that one is less than I is less than equal to n. And the meaning of this is X belongs to the union I goes from 1 to n A intersection B. Correct? So because every step is if and only if, we have proved, therefore LHS is subset of RHS and RHS is subset of LHS equal. Okay, I mean this is very easy and clear. Next, second thing is A union intersection I goes from 1 to n bi is equal to intersection I goes from 1 to n. A union bi. That means union distributes over intersection. First one was intersection distributes over union. Second is union distributes over intersection. Write down exactly similar question. All 1, 2, 3, 4, 5, 6 steps. Let X belongs to A union intersection I goes from 1 to n bi. If and only if X belongs to A or X belongs to intersection I goes from 1 to n bi. If and only if, what does this mean? It means X belongs to A or X belongs to bi. It is in intersection, therefore it has to be in every bi. For all I, 1 is less than equal to I less than equal to n. What does this mean? It means X belongs to A union bi for all I 1 less than equal to I less than equal to n. Correct? And then what does that mean? It means X belongs to intersection I is equal to 1 to n A union bi for all I. This is RHS. So LHS, subset of RHS, and RHS is subset of LHS. So this is important. We will require this in probability in the end. Now, true or false? Question 1. A union B is equal to A union C implies B is equal to C. Question 2. A intersection B equals A intersection C implies B equals C. What are your answers? Both are not true. Why? Counter examples we should have. A is equal to X comma Y. B is equal to X. C is equal to Y. So what is A union B? X comma Y. What is A union C? X comma Y. But is B equal to C? No. B and C are different. So this is false. And I mean, if you have A, B, C distinct, A, 1, B, 2, C, 3. A intersection B empty set is equal to A intersection C empty set. Therefore, B is equal to C false. You can create as many examples as you want, but the idea is very simple. Definition. A minus B is difference of two sets A and B. Is defined as A minus B is equal to all those x such that x belongs to A and x does not belong to B. So if we want to draw a Venn diagram, we have A, we have B, all those A's, all those x's which belong to A but does not belong to B. This is A minus B. This is B minus A. So can we write down A minus B in terms of our friends intersection union? A minus B is equal to A intersection B complement. B complement is rest of B and A, its intersection is A minus B. B minus A is equal to B intersection A complement. X is a universal set. I mean, these are easy things, but we require this for doing algebra eventually. Therefore, I am writing them. X is a universal set. A dash is equal to X minus A, which is X intersection A dash. B union X is equal to X. B intersection X is equal to B. B union empty set is B. B intersection empty set is empty set. Let A comma B belong to X universal set. We define symmetric difference. Denoted by delta as A delta B is defined as A minus B union B minus A. So, if we are defining symmetric difference like that, then in the Venn diagram, which particular elements are we talking about in symmetric difference? in symmetric difference, we are talking about A minus B is this, and B minus A is this. So obviously, what does this mean? Is meaning of this is you have A union B with you, and from A union B you subtract A intersection. That is what is also the meaning of symmetric difference. Question. What is A delta A? What will be A delta A? Symmetric difference of A and A. Of course, it will be tell me what is that? Obvious. Now, A delta B, true or false? Is equal to A delta C, implies B is equal to C. If true, write proof. If false, give counterexample. Okay. So as to solve this problem, A delta B is equal to A delta C implies B is equal to C, true or false, we will require this property, and I want you to prove this property, if true, of course, using Venn diagram, and then we will spend good amount of time to write the algebraic proof of this also. So, but right now you can do it using Venn diagram. So try to prove A delta B delta C is equal to A delta B delta C. Okay. So let us write down, let us try to draw LHS for this property. A, V, P. Okay. So B delta C is, B delta C is okay. Let me deliberately not color this because it comes. Sorry, this is A delta B. Let me draw A delta B first. I am deliberately okay. Let me complete by this color A delta B. This is A delta B. Okay, and delta C. That means we are supposed to add this quantity and remove this quantity and add the intersection. Is this the RHS and LHS both? Correct. This is going to be the diagram for LHS as well as RHS. Therefore, this is true. Okay. So if this is true, then let us solve the first. A delta B is equal to A delta C given. So you can take A delta B is equal to delta A delta C. You can take symmetric difference with the set A of both sides LHS and RHS. Now using this property, you can flip that delta B is equal to A delta C. This implies A delta A you said is empty. Empty delta B is equal to empty delta C, and empty delta B is equal to B, and empty delta C is equal to C. So the statement is true. Okay. Now we will do what do we mean by power set, and then I will give you sufficient time to prove this result algebraically. Okay.
Sir,
Yes.
in the diagram,
Okay. Let us understand what do we mean by power set. Power set of A. Let A be subset of universal set. Power set of A is defined as set of all those sets B which are subsets of A. So power set is defined as all those subsets B which are subsets of A. Example, let A be PQR, 3-element set. So power set of A is all possible subsets of A. So first possible subset is empty set. Second possible subset is of one element. I think we have done this in combinatorics. Then all those sets which have two elements. And a set which has three elements. This is the power set of. So number of elements of a power set.
Sir, pick donda
Huh?
pick donda.
हे दोनदा कसं झालं? अच्छा. मायक्रोसॉफ्टला ना व्हाईट बोर्डला चुलीत घालायला. Okay, so number of elements of power set of A in this case is 8, which is 2 raised to 3. So if A has n elements, so instead of writing that way, we can write it n of A is equal to say k elements, then number of elements of power set of A is equal to 2 raised to simple combination. Okay, Now I want you to prove that property A delta, I mean associative property, to prove algebraically. Let me just remind you about the tools that will be required. First tool is A union B complement is A complement intersection B complement. Second tool, A intersection B complement will be equal to A complement union B complement. Third tool that you will require is A intersection B union C is equal to A union B intersection A union C. Fourth tool that you will require is A union B intersection C is equal to, अरे चुकलो तो गई हो, union distributes over intersection and intersection distributes over union. पहिला मी लिहिलेला आहे A union B intersection C is equal to A union B intersection A union C. Then A intersection B union C is equal to A intersection B union A intersection C. Fifth thing that you will require is A union universal set X is equal to X. Sixth thing that you will require is A intersection universal set X is equal to E. Seventh thing that you will require is A union empty set is equal to A. Eighth thing that you will require is A intersection empty set is equal to empty set. Ninth thing that you will require is A delta B is equal to B delta A. That is why it is symmetric. 10th thing that you will require is A minus B is equal to A intersection B complement. Okay. 11th thing that you will require is A delta B is equal to A intersection B dash union A dash intersection B. And last thing, 12th thing that you will require is complement of A is A. Okay, so these are the tools. Prove that symmetric difference is associated. Let us write down. Let us start writing LHS. A delta B delta C is A intersection B delta C complement union A complement intersection B delta C. Correct? This is the first step. Second step. Let us write meaning of this delta also. So A intersection Meaning of this delta is B intersection C complement union B complement intersection C, correct?
Yes.
Then this bracket complete union second bracket open A complement intersection, meaning of this maybe rectangular bracket B intersection. I think I missed the complement here. Complement. This is complement. This complement comes here. So this is B intersection C dash union B dash intersection C. Rectangular bracket complete, normal bracket complete. Now, because we have complement here, we need to get rid of that complement, and when complement goes inside, union becomes intersection. So A intersection B intersection C dash complement intersection B dash intersection C complement. Okay, I mean we will have to bear with this now. So I have got this complement going inside. That is our first bracket union second bracket. Now I can distribute intersection over union. So A intersection B A dash intersection B intersection C dash union A dash intersection B dash intersection C dash. Okay, this bracket complete and another bracket. So now you can see that these two terms A dash intersection B intersection C dash union A dash intersection B dash. Right. Sorry, this should be C only. B dash intersection C. So two are complements, one is normal. That is what these two brackets are. So further simplification of these two brackets is not available. Okay. So now let us concentrate on the first bracket. What do we have? We have now let us distribute intersection. Now let us first get rid of this complement here and complement here, because both of them are complements. So A intersection rectangular bracket, when complement comes inside, it becomes B complement and union C intersection. When that complement comes inside, it will be B union C complement. Okay, union these two brackets, union this bracket, same. Now is equal to A. Okay, let this is intersection, this is this is union. So A intersection. Now this identity B complement union C intersection B. So this intersection B union this intersection C dash. Okay, one more rectangular bracket and one normal bracket is over. This is, I think, union, these two brackets, union, same. Okay. Now we distribute this intersection over union. So we get A intersection inside bracket, B intersection B dash, union B intersection C. Correct? This is first.
Yeah.
This is first. Let me have one more bracket here. So first bracket is complete. The union, second bracket, C dash intersection B dash, union C dash intersection C. Rectangular bracket complete, bigger rectangular bracket complete, and normal bracket complete. Union bracket, union bracket. Okay, I think we are done now. So the last thing that we would like to do is distribute. Okay, this is clear. Okay, what is the meaning of B intersection B dash? This is empty. So A intersection rectangular bracket. This is empty, union B intersection C. So practically it is B intersection C, union. Again, C dash intersection B dash will survive. C dash intersection C will become 0, empty. Dash intersection C is empty. So this is C dash intersection B dash. That is what we are left with. Union, this is this bracket, union, these two brackets, as it is. Okay, so now it is trying to distribute intersection over union. So A intersection B intersection C, union A intersection C dash intersection B dash, and what we left was union A dash intersection B intersection C dash, union A dash intersection B dash intersection C. Okay, the small brackets inside can be removed now because intersection is all three of them. We are supposed to take intersection of all three of them. Therefore, this is A intersection B intersection C. All three without complements. Union original A with BC complement. Original A B with AC complements. Original C with AC. So this is symmetric with respect to A, B, C. Therefore, LHS equals RHS. And now, if you are not happy with this symmetric with ABC, you might as well expand the RHS and get this same identity. Therefore, it is associated. Symmetric difference is associated. Maybe write down. Okay, and let us begin with relations. Definition: a relation from non-empty set A to a non-empty set B is a subset of product A cross B. Now, writing definition is one part, understanding definition is another part. Suppose A, ABC, B, 1, 2. So let us first write down A cross B. A cross B is all possible ordered pairs. A comma 1, A comma 2, B comma 1, B comma 2, C comma 1, C comma 2. This is your A cross B, and any subset of this is a relation. So R is, we can say R is A comma 1, B comma 1. Let us say this is R1. R2 could be A comma 2, C comma 1, B comma 1. This is what is relation. Relation is from, of course, non-empty set A to non-empty set B. This is called domain. This is called codomain. And you select any subset of A cross B. Question: if A has P elements and B has Q elements, then A cross B will have how many elements? P into Q each. And number of possible relations, or maybe number of relations, not possible. How many? 2 raised to P. I mean, you can create how many subsets of this set A cross B. It is like power set. Power set is set of all possible subsets of A cross B. So how many elements in the power set of A cross B? 2 raised to P. I will pause for a moment. So as far as relation is concerned, you can choose as many pairs as you want and create your own relation out of A cross B. No further rules, no further compulsions. So that relation is going to be little different than functions. Functions we have already seen the definition many times. We will write it again after some time. But relation is any subset of A cross B. Okay. So if we want to write down suppose a numerical example, we can write it in a couple of forms. This is what your set, listing form of writing set. It in the form of in roster form. Okay, so suppose A is 1, 4, 5. B is 1, 2, 7. And we want relationship R, all those ordered pairs X, Y, such that X is less than Y. X belongs to A, Y belongs to B. I mean, this could be another definition of some relation R. Okay. So we can always map it using diagram, domain, codomain. They are supposed to be ellipse. Hmm. 1, 4, 5, 1, 2, 7. Okay. So what we want is x to be smaller than y. So you can have this relation. Only one-sided arrow actually. Okay. You can have this relation. You can have this relation. And you can have this relation. So there are 4 elements in this particular relation. Okay. Now, without wasting much time, let me give you some definitions in relation, because in mains you may end up having some questions on relation, and therefore we need to do it, because if we ignore and you do not understand the meaning of any letter or word, then you are in trouble. So, types of relations. First, empty relation. Simple, no element of A is related to any element of B. Because see, you can choose a subset of this A cross B. You can always choose empty set as a subset. That is what is empty relation. No element of A is related to element of B. Second, universal relation. Each element of A is related to every element of B. Now, okay, that means A cross B is a universal relation. This itself is a relation and it takes care of all possible ordered pairs. Universal relation. Many other times only one set is given to you and you have to use the same set as domain as well as codomain. 3. Inverse relation. We understand this. If R is a relation, then R inverse is all possible ordered pairs B comma A, where A comma B belongs to relation. I mean, just come in the opposite direction. That is inverse B comma, all those B comma A's where A comma B's are part of the relation. So, domain of R is equal to codomain of or a range of R inverse. And range of R is equal to domain of R inverse. This will happen in inverse relation. Fourth, identity relation.
Excuse me, sir.
Yes.
Sir, what is the meaning of range of R inverse?
Range of
R inverse.
R inverse. Okay. Range of R inverse means when you are coming back from B to A, which particular values are attained all those A's is a range of R inverse. Range is all the values in the codomain which are attained. They receive arrow. So when we are talking about R inverse, that means we are moving from set B to set A, and all those values which are attained by R inverse is a range.
Thank you.
Okay. Identity relationship. Let A be the set. The relation IA, identity A, is all those ordered pairs A comma A, sorry, A comma A, such that A belongs to capital A. Okay, so the element should be same in both the places. That is called identity relation. So suppose set A is 1, 2, 3. Then the relation IA is equal to 1, 1, 2, 2, P3. But if at all, if you have, suppose another relation R1 is there, which has 1, 1, 2, 2, 3, 3, and some more element, 1, 3. Then R1 is not identity. Okay, so essentially in identity relation, you have to have all the possible ordered pairs which are same numbers, A comma A. So that means all possible means, suppose you have another relationship R2 where you have only two of them, then this is also not identity. Okay. You have to remember this. This is something which is notation or definitions or vocabulary of relations. Okay. Now, many times questions are asked on next three. Let us do it bit systematically. My handwriting is what a word. Microsoft Whiteboard. Fifth point. Reflexive relation. Reflexive relation. Okay. Let me write down the technically correct definition. A relation R on set A is said to be reflexive if A comma A belong to R for every A belonging to capital A. A relation, immediately after that, let us write a relation R on set A is not reflexive if there exists an element element A belonging to A such that A comma A does not belong to R. Okay, example. Let A be 1, 2, 3. Let R be 1, 1, 2, 2, 3, 3, 1, 3, 2, 1. Is this reflexive? Yes, is reflexive because it satisfies the definition. Here, does it contain A comma A for every A? Yes, it is there, it is there, it is there. What else is there does not matter. But it is not identity relation, because in identity relation you will not allow these two ordered pairs. So this is reflexive relation, and if you write this, say R1 1, 1, 3, 2, 2, 1, 3, 2, not reflexive.
Sir,
Yes.
it should be A comma A not belonging to R, not A comma B.
Here,
Yes,
should be
A comma A.
yes. I unconsciously I write that as B somehow. I don't know why. But the moment I am writing ordered pair, it see now also I was about to write B.
सर ते दुसरा सेट का नाही चालत दुसरा सेट का नाही चालत
कारण ऑल नाही आहेत ना फॉर एव्हरी सी फॉर एव्हरी ए belonging to A there has to be that ordered pair. That is the meaning of this symbol.
कळलं.
Now another thing you can observe that whenever I am writing relation R, I am writing real number R. That is also, it is muscle memory which is acting over there. So I have to, whenever I am writing capital R, I write it like real numbers. Okay. So this is one part of the story, and you have understood what is reflexive. Transitive 6. A relation R on a set A is said to be transitive if A1 comma A2 belonging to the relation and A2 comma A3 belonging to the relation implies A1 comma A3 belonging to relation. For all A1, A2, A3 belonging to A. Example. I mean, it is transitivity type of thing is happening there. If A1, A2 is part of relation, A2, A3 is part of relation. If that implies A1, A3 is also part of relation, then the relation is said to be transitive. Say, for example, a set of natural numbers, A, B, set of natural numbers. If R is defined as, if R is defined as X less than Y, then A will be less than B and B will be less than C, will imply A is less than C, that is A comma B belong to R, B comma C belong to R, implies A comma C belong to R. Hence this relation, which is defined by X less than Y, is transitive. That is all about it. 7. Seventh in black, 7th in black. Select black, yes. Symmetric relation. A relation R on set A is said to be symmetric if A1 comma A2 belong to R, implies A2 comma A1 belong to R. For all A1 comma A2 belonging to A. Consider example. Consider set A, B, set of natural numbers. If relation R is defined as X plus Y is equal to 5. because addition is commutative, you will end up having symmetry. Y plus x is also going to be equal to. So say 3 comma 2 of course belongs to R, implies 2 comma 3 will belong to R, for example. Hence symmetry. Okay? No. I am assuming that you are understanding because it is very simple. Okay? What happened to this? Verb, verb, verb. Verb. Last one. Equivalence relation. A relation R on set A is said to be equivalence relation if R is reflexive, symmetric, and transitive. Then it is called, if all three of them are there together, then it is called equivalence relationship. Show that relation R in the set of question. Relation R in the set of real numbers defined as R is equal to all ordered pairs A comma B such that A is less than or equal to B square is neither reflexive nor symmetric nor transitive. So this is an example where equivalence relationship is not there. Do I have any example where equivalence relationship can be shown? Yes. Now it is easy to prove that. Question 2. Show that the relation in R in the set A 1, 2, 3, 4, 5 by relation R is equal to all those ordered pairs A, B such that absolute value of A minus B is even is an equivalence relation. Okay, so do these two problems and we are done.